Most of the antennas which radio amateurs use on HF, VHF, UHF bands have linear polarization, either vertical or horizontal, and are not ideal for satellite communications. Polarization of an antenna is the direction of electric field produced by the antenna and determines the direction of transmission and reception. In circular polarization, the radio waves rotate as the signal propagates. If it rotates to the right, it is known as right-hand circular polarization, RHCP, and if it rotates to the left, as left-hand circular polarization, LHCP. Using circularly polarized antennas helps to minimize the effects of cross-polarization losses as the satellite moves through space. Even if the satellite antenna is vertically polarized, the signal changes direction as the satellite tumbles and spins in orbit. Cross-polarization means polarization of the transmitting antenna and receiving antenna are at right angles to each other, producing great signal loss near to total in ideal conditions. If your antenna is circularly polarized, the signal loss will not be total when the satellite tumbles and spins in orbit. Difference in signals received between right and left hand circular polarization will be only 3 dB, unlike that between horizontal and vertical polarizations, which could be near total loss of signal regardless of how much power is used. Often amateur radio satellite builders use circularly polarized antennas on them. A popular form of omnidirectional antenna for a base station is known as egg beater antenna because the shape resembles an actual egg beater used in the kitchen. Another type of antenna with circular polarization is a quadrifilar helix antenna. Gamma impedance match for the antenna is also known simply as gamma match. In case of a Yagi-Uda type of antenna, it allows the driven element to be a single rod or tube without being cut at the feed point, giving more physical integrity to the system. As the RF voltage at the center of a half-wave antenna is 0, the outer sleeve of the coax can be connected here, which corresponds to the position on the boom as well. The central conductor of the coax is then connected beyond the center point through a capacitor to tune out the inductance of connecting arm of antenna. The name gamma match comes from the resemblance of the shape of connection region to the Greek alphabet gamma. As the gamma match forms an unbalanced system, it can be connected to the coax without a balun, as both the coax and the antenna are unbalanced in this case. Capacitor in the circuit is initially a variable capacitor, which is replaced by a corresponding fixed value capacitor after tuning. Gamma match is often used for an HF antenna and sometimes for a VHF antenna. When fed by a 50 ohms unbalanced coax feeder, length of the gamma rod is about 5% of the wavelength. Its diameter is typically half that of the driven element. Spacing between the gamma rod and the driven element is about 0.7% of the wavelength. Value of the capacitor will be about 7 picofarad for a meter of the wavelength. In a folded dipole antenna, a half wavelength conductor is folded into a longitudinal loop and fed at the center. It has a higher impedance of around 280 ohms compared to the 70 ohms impedance of a horizontal half-wave dipole antenna. Hence, while a coaxial cable is suited for a horizontal half-wave dipole antenna, a twin-lead transmission line with about 300 ohms impedance is used for a folded half-wave dipole antenna. Half-wave folded dipole is commonly used as the driven element of a Yagi multi-element antenna. Like a half-wave dipole antenna, the folded dipole is also resonant and radiates well at odd integer multiples of half wavelengths. As mentioned in case of half-wave dipole antenna, it acts as a 3/2 wavelength dipole at 3 times the fundamental frequency. Folded half-wave dipole antenna is preferred when the impedance has to be higher. Folded dipole antennas were a common sight on rooftops as part of Yagi-Uda television antennas in the past. Now, with cable television becoming more popular, we seldom see any folded dipole antennas on rooftops in my region. Still, folded dipole antennas as part of Yagi-Uda directional beam antennas are popular among radio amateurs who operate on VHF and UHF frequencies of the radio spectrum. Viewing from a homebrewer's aspect, it is technically more difficult to make folded dipole antennas as you have to bend the aluminum tubings usually used for such antennas at right angles twice on both sides. Hence, I am yet to venture into homebrewing of a folded dipole antenna. Folded dipole can be considered as a dipole antenna on top of which a loop of conductor is added so that it will be short-circuiting any direct current fed to the antenna, though antennas are typically fed with alternating currents. Folded dipole is a balanced antenna and has to be fed by a balanced feeder like a twin-lead ladder line. If a coaxial cable is used to feed the folded dipole antenna, a balun or balanced to unbalanced transformer has to be used. While the usual half-wave dipole antenna has an impedance of about 70 ohms, folded dipole antenna has an impedance of around 280 ohms. So it matches well with a ladder line of 300 ohms impedance. Earlier, twin-lead ribbon tapes were used to connect the folded dipole antenna to the television receiver. Folded dipole antenna has a higher bandwidth than the usual half-wave dipole antenna. There can be variants of the dipole antenna in which the additional conductor loop can have a different thickness with a change in the feed point impedance. Another implementation is adding another loop on top of the first loop so that 3 longitudinal regions are there for the folded dipole. Such multi-conductor folded dipoles can have an impedance of 600 ohms instead of the 300 ohms of the standard folded dipole. Bandwidth is higher for such folded dipoles. One reason for using folded dipoles instead of usual dipoles in Yagi-Uda antenna is to increase the impedance. When parasitic elements are there close by, the impedance of a standard half-wave dipole antenna may be reduced, sometimes making matching difficult. Another reason for considering folded dipole as part of Yagi-Uda antenna is to increase the bandwidth in order to cover a full amateur radio band. Radiation pattern of a folded dipole is similar to the standard half-wave dipole in a figure of 8 pattern in the E-plane. As the 2 conductors are near each other, the folded dipole is considered like a single conductor of half wavelength and has a directivity similar to half-wave dipole. The distance between the conductors is small compared to the wavelength of the operating frequency. Bazooka antenna is a coaxial dipole antenna with the main part made of coaxial cable. It was originally designed by the staff at Massachusetts Institute of Technology for radar use with coaxial cable for the entire radiating elements. Adaptation for ham radio uses coaxial cable only for the broadbanding portion, while ladder line is used for the rest of the antenna. Bazooka antenna is a single band antenna with a broad bandwidth within the band, unlike the dipole which has only a bandwidth up to 100 kHz. Moreover, Bazooka antenna does not radiate harmonics of the operating frequency and feed line radiation is very little. Bazooka antenna modified for ham radio uses does not need a matching balun and can be directly connected with 50 ohm coax. As the antenna has no exposed metal wire, static charges do not build up and reduces noise compared to exposed wire antennas. Bazooka antenna consists of a half wavelength coaxial line with outer conductor cut at the center and the feed line connected to the cut ends of the outer conductor. Inner conductor is not cut and does not radiate. It acts as a quarter wave shorted stub and serves to increase the bandwidth by cancelling reactance at off-resonant frequencies. Central conductor and shield of the antenna element coax are soldered together at both ends, shorted. Two wires of the ladder lines are soldered to this joint on both sides of the coaxial antenna elements. The other ends of the ladder lines are also shorted by soldering the wires together. K5IJB has provided calculations of lengths of the coaxial cable segments and twin lead segments for various amateur radio bands from 40 meter to 6 meter. J-pole antenna is quite popular among radio amateurs for 2 meter and 70 centimeter bands, that is the VHF and UHF bands. It consists of two segments, one 3/4 wavelength segment and a matching stub, which is a parallel shorted matching stub of quarter wavelength. The portion above that is corresponding to the portion beyond the quarter wave, will be a half wave. This is a half wave, and another quarter wave is attached here. And for this half wave antenna, up to this, when the coax is fed here, it can be considered as a unfed antenna. Unfed antennas have high impedance, and this requires a matching. So this arrangement of the J-pole is mainly for matching. You have connections from the coax on either side, and the connection point has to be adjusted by sliding up and down to have the lowest SWR. That is how the J-pole antenna is tuned. J-pole has a gain of around 2 dB above a ground plane vertical antenna. This region between the two elements, between the shorting stub and the matching stub and the main element, should be less than 2% of the wavelength. And the whole assembly should be away from conducting material. You should not have metallic structures near this. If you are using a galvanized iron pipe, as is usual among us radio amateurs, then a section of non-conducting material like a wood piece or PVC pipe has to be attached below the antenna, between the antenna and the mast. And the length of that should be at least about 3 times of this separation between the two elements. And there should not be any other conducting material near this, like a window grill or another mast should not be very near to this antenna for best performance. And J-pole antenna has a little higher gain in the direction of the quarter wave matching stub. And this antenna has been used for terrestrial communication through repeaters and simplex operations, as well as for satellite communications. In satellite communications, if you have a VHF antenna, usual amateur band for UHF, ultra high frequency, is on the 3rd harmonic of our VHF band. In satellite communication, usual amateur 2 meter band and amateur 70 centimeter band are like 3rd harmonic. That is, a 2 meter antenna will also resonate as 3rd harmonic on the 70 centimeter band. So this can be used as a single antenna for satellite communication for favorable passes. This is just like you use a 7 megahertz dipole antenna for 21 megahertz also, with a reasonably good standing wave ratio or SWR. Similarly, this can work for as a dual band antenna also, though not optimal. And it is also mentioned that when you use J-pole, 2 meter J-pole for 70 centimeter, the angle of radiation is not ideal for terrestrial repeaters or terrestrial communication, but it is okay for satellite communication. A slightly different angle of radiation directed towards the satellite is there compared to that of the terrestrial repeaters. So a single J-pole antenna on 2 meter has been successfully used for satellite communication for the crossband repeater. You know that International Space Station and many other satellites have VU transponders with uplink on VHF and downlink on UHF. So if single antenna works for both, that's convenient for the operator. That's meant for those who are operating using base station from within the shack. This diagram shows the current and voltage pattern, that is the RF current, not DC current, RF current pattern in the stub and the other main segment of the antenna. You can see that the current is peaking at the lower end and also at the quarter wave region. This portion will be a quarter wave. Peak is at lower end and also at the quarter wave segment. And at the top, the current is minimum, RF current is minimum. Voltage is the other way around. Voltage is maximum at the upper end and for the lower 1/3. Here also the voltage is peaking. And in case of the quarter wave step, voltage is peaking at the upper end and current is peaking at the lower end. This is the current pattern in the two regions of the J-pole antenna. This diagram illustrates the radiation pattern from a J-pole. So as you can see, slightly higher towards the matching stub region. And a slightly higher angle would mean that it will be directed towards the sky partially, and that is how this is useful in satellite communications. You want the radiation to be slightly on a higher angle towards the satellites in the sky. Of course, a single J-pole antenna is not the ideal one for satellite communication because this will not have a high gain, and being omnidirectional, the whole of the radio frequency which you radiate from the J-pole will not reach the satellite. Only a small fraction will reach the satellite. Unlike in case of Yagi antenna, which has a high front to back ratio and directivity, most of the signals would reach the satellite. While here, as the radiation pattern is omnidirectional, only a small portion will reach the satellite. But still, this is a compromise antenna for satellite operation because you don't have to rotate the antenna. If you don't have an antenna rotator, Yagi antenna will work only during a very small portion of the satellite pass, while J-pole will work almost throughout the pass. So rotator is not needed, or rather other way around. If you don't have a rotator, you can consider J-pole as a compromise antenna for satellite operations. Then a single antenna for both UHF and VHF is also a compromise. Ideal would be to have two J-poles, one for UHF and VHF, and then connect with a diplexer to the radio. But all getting things complicated for a beginner in satellite operations. With the J-pole, you may be able to operate some of the good passes of satellites, but no low elevation passes, and also you are unlikely to get any DX using an omnidirectional antenna unless you are lucky to be on the top of a high-rise building at a high altitude, and then you might be able to work. If you are on a mountain, on a high-rise building, even a J-pole you could work comfortably a lot of DX. That's a very rare situation. Connecting an external monitor is useful to see the screen of the FT710 amateur radio much more clearly than in the small TFT screen of the radio. Only DVI-D monitors and cables are compatible with FT710. Though it is possible to connect an HDMI monitor with a DVI-D to HDMI converter, one ham cautioned me against using it as it could lead to a blown fuse inside the FT710. If that occurs, sending FT710 back to the factory for repair is not an easy job in my region, as we do not have a branch of the manufacturer over here. So a DVI-D monitor and cable were bought online. But simply connecting it to the DVI port and giving power did not work. Function key of the radio had to be accessed to get the display settings and enable the external monitor. Pressing the function key brings the options on the TFT monitor, from which you can choose the option from the touchscreen function. As I had already connected a mouse to the Type A USB port at the back of the radio, I used a mouse for accessing on-screen functions. Though the initial setup is using the TFT screen, I am showing it again on the external monitor for better clarity. Display settings are seen at the bottom of the screen. On clicking it, the next screen will show the option to enable external monitor, which can be selected on TFT touchscreen. Here I am showing the selection using the mouse for the demo. There are only two options for the resolution in the radio, though the monitor can support higher resolutions. I have opted for 800 to 600 pixels format. The dialog box appearing on the external display can be closed only using the button at the lower part of the display, as it is a function of the external display. You cannot click the close option shown in red using the mouse. In this video clip, I am testing out some of the options on the external display using the mouse. Changing the mode from LSB to USB, accessing the attenuator, and changing attenuation levels and AGC are shown as examples. Only functions which are accessible on the TFT touchscreen of the radio can be accessed using the mouse on screen. For other functions, switches on the radio have to be used. There are several buttons and a function knob on the radio for initial access to bring them on TFT screen, like mode and band. As there is only one Type A USB port, only either mouse or keyboard can be connected at a time. Maybe a USB hub can be used to connect both together at the same time. But I am not trying to use it till I get confirmation from ham friends on some forum, as I have not seen it mentioned in the user manual. Here you can see the power cord, DVI-D cable and Type A USB cable attached to the back of the radio. This is a still picture of the Type A USB connector, DVI-D cable and power cord connector plugged in. Delta loop antenna is a full wavelength antenna in the shape of the Greek alphabet delta. The antenna forms a delta shape with limbs like an equilateral triangle. Though it can be made with base at the top, bottom or sides, practically it will be easy to have the base at the top as shown in the picture below. It will need a 4:1 balance at the feed point for impedance matching. Otherwise, the SWR, standing wave ratio, will be high. As with the half wave dipole antenna, a delta loop antenna for 7 MHz will also function well with the odd multiple frequency of 21 MHz. On 14 MHz, the antenna impedance is high and SWR will be high. For the sender of 7 MHz amateur radio band with frequency of 7.1 MHz, the length of the delta loop will be 43.14 meter. Delta loop antenna is fairly easy to construct if you can put up two strong poles. Recommended height is above 18.3 meters for a 40 meter antenna, which comes down to 4.6 meter for a 15 meter delta loop. Rybakov 806 is a vertical antenna supported by a telescopic fiberglass fishing rod, which gave it the name Rybakov, which means fisherman in Russian language. The suffix 806 is probably because it is a broadband antenna which can cover from 80 meter to 6 meter. IV3SBE, who designed it, describes it as a little miracle which is only 1.6 meter when not in use and 9 meter when fully extended and weighing only 2.2 kilograms. 8 meter wire is used with a 4:1 union at the feed point. Union by definition matches an unbalanced antenna to an unbalanced feed line. Here it is used to lower the impedance of a random wire antenna. Rybakov 806 vertical is a highly portable antenna popular for field operations. Though the length of the wire is not critical, resonance at bands of interest is avoided. As it is a non-resonant antenna, an antenna tuner is a must. Built-in antenna tuners of modern radios may be enough. A wire length of 7.6 meter can cover from 7 MHz upwards. If 3.5 MHz is needed, wire length has to be increased. Some sort of a ground or radial has been recommended. WB3GCK mentions a 25-foot radiator and a 25-foot radial. Extension of radiator to 53 foot for 80 meter operation was suggested. Recently, I installed a CP22E antenna, which is a stacked 2-element 5x8 lambda vertical antenna with a phasing coil in between. 5x8 lambda vertical antenna has a length a little more than the usual quarter wave length vertical antenna. It has a similar low angle of radiation useful for local contacts. Hence, it is a popular form of mobile antenna which can be mounted on a car. Mounting can be with a magnetic base so that it avoids drilling the car chassis, with obvious advantages when you consider resale of the car. Matching coil is provided at the base of the antenna to give good impedance matching like that of a 3/4 lambda vertical antenna. Under ideal conditions, 5x8 lambda vertical antenna has a 4 dB gain over a quarter wave vertical antenna. When it is mounted on the car body acts as the ground plane. 5x8 lambda vertical antenna mounted on a car is typically used for VHF and UHF amateur radios. It can be used as an HF antenna for a base station as well. In that case, the low angle of radiation will be useful for DX contacts. Standing wave occurs when there is impedance mismatch between the transmission line and the load, which is the antenna. When there is an impedance mismatch, part of the signal is reflected back to the transmitter. This reduces the effective power transmitted and thereby the efficiency. Standing wave can be considered as a resultant of forward and reflected waves together. Standing wave ratio, or SWR, is the ratio between the maximum and minimum amplitudes of the standing wave. Highest level of SWR occurs when the antenna is not connected open circuit or when there is short circuit in the transmission line. SWR can be in terms of voltage, known as voltage SWR, and current, known as current SWR. Usually, it is the voltage SWR that is measured using an SWR meter. Ideal SWR is 1 and high SWR above 2 can cause heating of the transmission line and final power amplifier of the transmitter circuit and likely to cause severe damage. Duct propagation is a special type of propagation around the curvature of the earth even as much as 1000 kilometers at VHF and UHF frequencies. This occurs when there is a temperature inversion in the troposphere. In temperature inversion in that region, the temperature increases with height instead of decreasing. This leads to refraction of higher frequencies down to Earth instead of going up into the ionosphere. Reflection from the ground back to the troposphere initiates a similar process again. This has been called duct propagation or super refraction. Duct propagation allows the signals to pass beyond the horizon, unlike the usual line of sight propagation of VHF and UHF frequencies. The atmospheric duct in case of duct propagation acts like a natural wave guide in the atmosphere, which guides radio waves along the curvature of the Earth. The atmospheric duct is a region of cool air between two layers of warm air above and below, between the troposphere and the stratosphere. As cold air and warm air have different densities and hence refractive indices, the radio waves received at a low angle get refracted downwards instead of penetrating up into the ionosphere and above. Cool air has a higher refractive index. The signals are thus trapped in the atmospheric duct and propagate along the curvature of the Earth beyond the usual line of sight between the transmitting and receiving antennas. Though this is a benefit for increasing communication distance, radar systems can sometimes be adversely affected by the presence of atmospheric ducts. Yet, it could be useful for over-the-horizon radar systems. Digital mobile radio, known in short as DMR, is the digital counterpart of conventional analog radios. It uses time division multiple access or TDMA technology for transmission. As it uses TDMA technology, it can operate two slots in a conventional 12.5 kHz channel spacing. European Telecommunications Standard Institute or ETSI created the DMR standard in 2005, which has been revised several times as late as 2018. DMR can operate both in the very high frequency or VHF range, which is between 30 MHz to 300 MHz, and the ultra high frequency or UHF range between 300 MHz to 1 GHz. As in the case of analog transceivers, DMR range can be extended using repeaters. Repeaters could be linked to each other using internet to provide global coverage. ETSI has envisaged 3 tiers for DMR, of which Tier 1 is license-free in most countries of the European Union in a specific band. Tier 2 needs license and is for frequency bands from 66 to 960 MHz. Tier 3 is for trunking in the same spectrum and supports voice and short messaging. Tier 3 also supports packet data with support for Internet Protocol version 4 IPv4 and Internet Protocol version 6 IPv6. An article on DMR in Wikipedia mentions that Federal Communications Commission of the United States of America (FCC) officially approved the use of DMR by amateurs in 2014. But a search on digital mobile radio at the FCC website did not return any results on 21st January 2023. So I am not sure on the status of use of DMR by radio amateurs. Another advantage mentioned for DMR over analog radio is the added security provided by authentication and encryption. DMR has also facility for location using Global Positioning System (GPS). This has been touted as a boon if you lose your way in a remote place. Other potential advantages of DMR are a clearer audio and better battery life. Dipole antenna is a vertical omnidirectional antenna popular among ham radio operators for 2 meter and 70 centimeter operations. As it is an end-fed antenna, the feed point of the half-wave segment of the antenna will have high impedance, which has to be matched to the feed line by a shorted quarter-wave parallel transmission line stub. The point of attachment of the feeder coax is determined by sliding the connection back and forth along the stub, monitoring for the lowest SWR. J-pole antenna has a gain of about 2 dB compared to a quarter wave ground plane antenna. The gain is slightly more on the side of the J stub compared to the opposite side. Parallel conductors of the J-pole antenna should be kept away from other conducting material by a distance of 2 to 3 times the spacing between the conductors. Best performance is obtained by having a non-conducting free space between the antenna conductors and the mounting structure. Separation between the two conductors should not be more than 2% of the wavelength. An important advantage of the J-pole is that it does not require radials or a ground plane. This reduces the wind resistance. A coil of coax at the feed point can serve as a choke to prevent radio frequency from traveling down along the feed line. There are several versions of multi-band inverted L antennas out there. I thought of describing a center-fed one and an end-fed one. Center-fed one has been described by W4RNL and end-fed one by VK6YSF. A center-fed inverted L for 80 meter would be 65.5 feet tall and having a horizontal limb of 65.5 feet. Lowest end of the antenna will be 4.5 feet off the ground. As it is a complete dipole, it does not need a ground plane beneath it, unlike a quarter wave antenna. A parallel feed line of 450 or 600 ohms impedance and an antenna tuner are needed for multi-band operation. The end-fed inverted L multi-band antenna is a portable one and uses 7 meter squid pole, which is a lightweight telescopic fishing pole. Antenna is a simple light wire of 18.7 meter length. It has been mentioned that wire length could be changed but should avoid quarter wavelengths and multiples of quarter wavelengths of the intended bands. 1:9 voltage balance is used to feed a 50 ohms connection. A horizontal 5 meter counterpoise wire is also needed. This setup can be used by connecting to an automatic antenna tuner. Hexbeam or hexagonal beam is a directional HF antenna popular among amateur radio operators for DX work and contests. 83K group of contesters for CQWPX contest 2023 from National Institute of Technology Karnataka had used Hexbeam for higher bands. The name comes from the hexagonal outer shape of the antenna. It looks like an upturned umbrella as well. In the original design by Mike Traffy N1HXA in 1996, both director and reflector had W shape or M and W to be more specific. The revised shape by Steve Hunt G3TXQ is shown in the figure with reflector half of a hexagon. The bending of the driver and reflector reduces the turning radius of the whole antenna compared to the Yagi-Uda antenna, which also works on the same principle. Lesser size would mean a lightweight antenna with obvious advantages on the mast and rotating infrastructure, avoiding the need for a hefty antenna tower. Multi-band Hexbeam antennas covering multiple bands like 20, 15 and 10 or more are popular. In multi-band Hexbeam, the elements for the lowest frequency are at the exterior of the antenna. Vertical spacing between the elements is critical as multi-band elements can influence each other if the elements are not parallel. Figure shows only elements of a single band for simplicity. Supports are made of non-conducting material while the elements can be of insulated copper wire. Hexbeam has a gain of 5 to 6 dBi and forward-reverse attenuation of up to 20 dB. Tropospheric scatter propagation is known in short as troposcatter propagation. Troposphere is the lowest layer of the atmosphere. Though troposcatter is typical at microwave or super high frequency or SHF band, It can also occur at VHF and UHF bands. The height of the troposphere is about 20 km near the equator, which comes to about 9 km in polar regions in summer. Height of the troposphere is more in summer than in winter. Troposphere can refract higher end of the radio spectrum. HF is reflected typically by the ionosphere, much above the troposphere. Tropospheric scatter was used mainly by the military prior to the era of satellites. When the transmitting and receiving stations point their antennas to a common scatter volume in the troposphere, as shown in the illustration, troposphere refracts the signal towards the receiving station. Troposcatter may work from frequencies as low as 144 MHz to 10 GHz, and useful communication can occur from 100 km to 700 km. Typically, the transmitting power has to be high and the receiver quite sensitive, as the signal loss is high in troposcatter. Yet, it is supposed to be a reliable mode of communication at the higher end of the useful radio spectrum. The angle between the two radio horizon rays is known as the scatter angle. The volume of intersection of the two beams is known as the scatter volume. Scatter volume will be high for low gain antenna with a wider beam and lower for a high gain antenna with a narrower beam. Full wave loop antenna is also known as self-resonant loop antenna and large loop antenna. Other loop antennas are halo antenna and small loop antenna. Perimeter of the full wave loop antenna is slightly more than a full wavelength of the operating frequency. It is quite efficient and can be used for transmission and reception. Small loop antenna is mostly used as a receiving antenna. Shape of the loop can be a circle, triangle, square, rectangle, or any closed polygon. A popular form of full wave loop antenna is quad antenna with a square shape constructed with a wire strung on an X-shaped supporting frame. Additional parasitic elements can be used as director and reflector. Such an antenna array will have unidirectional gain, which increases with each additional parasitic element, like a Yagi-Uda antenna. The antenna gets a diamond shape if mounted on a plus-shaped support. A triangular full-wave loop antenna is another form of a vertical loop which requires only one elevated support. In a special case of full-wave loop antenna, a rectangle which is twice as high as its width gives a better gain and can match 50 ohms directly if used as a single element. Different shapes of loop antennas will have different gains and impedances. Gain and impedance also changes with the location of the feed point on the loop. My Twitter contact G6AD uses a full wave loop of wire at 30 feet for 80 meters. It is coax fed to a 2:1 transformer. With that setup, he is able to work DX on 80 meter with 100 watts. Many radio operators use the term resonance and impedance matching interchangeably, but they describe two different electrical conditions. Confusing them can lead to misleading SWR readings, inefficient power transfer, and even damaged equipment. Here is the breakdown of why they are different and why both matter for your station. Resonance occurs when a circuit's inductive reactance and capacitive reactance cancel each other out. At this specific frequency, the antenna or circuit becomes purely resistive. Every antenna has physical dimensions that naturally resonate at a specific frequency, like a guitar string. When resonant, the antenna no longer pushes back energy into the circuit as reactance. The impedance is simplified to just the resistance. A resonant antenna does not automatically mean a 1:1 SWR. A resonant antenna might have a resistance of 15 ohms or 300 ohms, While it is resonant, it still won't match your 50 ohms radio. Impedance matching is the process of making the load, that is antenna plus feed line, look exactly like the source, your radio. Most modern ham radios are designed for a standard 50 load impedance. The goal is to maximize power transfer and minimize reflections. This is where antenna tuners' balance or matching stubs come in. They transform whatever antenna's impedance is into 50 ohms. You can match a non-resonant piece of wet string to 50 ohm using a tuner. The radio will be happy because of low SWR, but the string won't radiate efficiently because it is in resonance. Here is a comparison at a glance. Inductive and capacitive reactances cancel each other at resonance, while for impedance matching, load impedance and source impedance are matched, usually both are 50 ohms. At resonance, phase angle is 0 degrees. For impedance matching, SWR is 1:1. Main benefit of resonance is efficient radiation or absorption of signals for a reception. Impedance matching protects the final transistors. Resonance can be changed by change in physical length or size of the antenna. Impedance matching can be done using a tuner, balun or transformer. Now, why is the confusion? The confusion exists because at the sweet spot they happen at the same time. If you build a perfect half-wave dipole in free space, it resonates at a length where its resistance is roughly 72 ohms. If you mount it near the ground, the resistance often drops closer to 50 ohms. In this specific case, the antenna is both resonant, reactance is 0, and matched, impedance is 50 ohms. Here are a few fuller scenarios. 1. Resonant but mismatched. A full-wave loop antenna is resonant, but its impedance is about 100 to 120 ohms. Your SWR meter will show around 2:1 SWR, even though the antenna is perfectly tuned to the frequency. 2. Matched but non-resonant. Using a wide range tuner on an N-fed invisible wire, that is an N-fed thin wire stealth antenna, the tuner makes the radio see 50 ohms impedance, so the SWR is 1:1. But the wire itself is reacting wildly, often losing power as heat in the tuner or coax. To summarize, resonance is about antenna's relationship with the frequency. Impedance matching is about the antenna's relationship with the radio. For the best performance, you want to cut your antenna to be as resonant as possible for your target band and then use matching techniques to satisfy your radio's 50 ohms requirement. Yesterday, while I was contacting a friend at about 2500 km from here on 21 MHz, he told me that he was using a 20-meter delta loop antenna and it works on multiple bands even without a tuner, and I was quite surprised. Another friend on the other side of the globe told me online that his 40-meter delta loop antenna works on higher non-WARC bands with reasonable SWR. Wanted to know more about the multi-band capability of delta loop antenna. My Google search immediately brought me to a 40 to 10 meter multi-band delta loop antenna. General information is that delta loop antenna is a full wavelength antenna in the shape of the Greek alphabet delta. It will need a 4:1 balun at the feed point for impedance matching. If the delta loop is mounted vertically, the low takeoff angle of electromagnetic waves is good for working distant stations. If mounted horizontally, it is useful as near vertical incidence sky wave (NVIS) propagation for medium range communications in amateur radio, especially in hilly terrain, forest region, and even in cities with high-rise buildings. Another type of delta loop antenna is a multi-element delta loop antenna, which when compared to a Yagi antenna of same gain has a wider beam width. This could be an important advantage for working DX as well as contests. Multi-element delta loop antenna has directivity like the Yagi antenna, although it is practically difficult to construct for HF bands due to the dimensions. Usual single element delta loop antenna mounted in the vertical orientation has bidirectional radiation pattern along the broad side of the antenna. For example, if the base wire of antenna is north-south, direction of gain will be towards east and west, which can be up to 3 dB over a center-fed dipole antenna. Like other loop antennas, it is not only a good transmitting antenna, but also a low noise receiving antenna. Supplier of one commercially available multiband 40 to 10 meter delta loop antenna has mentioned that it cannot be operated by a coaxial cable. Any parallel wire feeder can be used to operate on 7 bands using a tuner. They have also mentioned that best results are achieved with a symmetric tuner, but any other tuner with a balun also works well. Others have used coaxial cable with 4:1 balun for multi-band operation. There are also descriptions of shortened delta loop antennas for those with space constraints. Commercial options for 3.5 to 54 MHz and kilowatt range rotatable ones could be seen as mentioned online. Yagi-Uda antenna is very popular in amateur radio or ham radio. It is also a common sight on housetops before the era of cable TV and satellite TV. It consists of a driven element and a variable number of parasitic elements on a boom. The driven element could be usual dipole or a folded dipole. Element behind the driven element is the reflector. Elements in front of the driven element are called directors. Typically, the reflector is longer than the driven element, while directors are progressively shorter than the driven element. Output of the radio is fed only to the driven element. Animation illustrates how a 4-element Yagi-Uda antenna works. There are 2 directors and a reflector in addition to the driven element dipole. The parasitic elements act as resonators by absorbing and re-radiating the electromagnetic waves from the driven element with a phase difference. There is constructive interference of these electromagnetic waves in the forward direction as they are in phase, and destructive interference in the reverse direction as the waves are out of phase. Net effect is a stronger signal in the forward direction and a weaker signal in the reverse direction. This is usually mentioned as the forward-backward ratio of the antenna. In the animation, the signals are color-coded similar to the antenna element for ease of recognition. Yagi-Uda antenna is often called as a beam antenna in amateur radio. Due to the size, it is less often used on HF bands than on VHF and UHF bands. The number of elements practically feasible are also lower on lower bands. They are used with antenna rotators as good directional antennas. Yagi-Uda antennas can have gains up to 20 dBi and a front-to-back ratio of up to 20 dB. Radiation pattern is linearly polarized with horizontal polarization for a horizontally mounted antenna and vertical polarization for a vertically mounted one. Bandwidth of Yagi-Uda antennas is relatively narrow, with a narrow range of frequencies within a band at which it has good gain and operable feed point impedance. The driven element or radiator can be a simple dipole with two quarter wavelength rods connected to either conductors of the feed line. In some versions, it is a folded dipole which has a higher impedance of around 280 ohms. The television antennas of yesteryears with folded dipole used to be fed using a twin lead transmission line with impedance of about 300 ohms. Folded dipole will need a matching for amateur radios with impedance of 50 ohms. Usual dipole has an impedance of around 70 ohms. Spacing between the elements may vary from quarter wavelength to 1/10 of a wavelength depending on the design. Radiation pattern of Yagi-Uda antenna is along the axis perpendicular to the plane of the elements towards the direction of the directors. As the parasitic elements have zero RF voltage at the center, they can be directly attached to the boom, but this will electrically shorten them and usually a correction in length is needed to cover this. There are versions in which all elements are insulated from the boom as well. The two halves of the center-fed dipole have to be insulated in the location of the boom. Helical antenna, as the name implies, is an antenna in which one or more conducting wires are wound in the form of a helix. It is typically used in VHF and UHF ranges, with the most common example in amateur radio as the rubber ducky of handheld radios. Helix can be found inside the rubber ducky when the outer covering is removed. If the helical antenna is made of a single wire, it is called monofilar, and bifilar if it has two wires, and quadrifilar if it has four wires. Helical antennas can operate in normal mode as broadside helical antenna or in axial mode as end-fire helical antenna. In the normal mode, diameter and pitch, or the distance between successive turns of the helix, are small compared to the wavelength. They function like electrically short dipole or monopole equivalent to a quarter wavelength vertical antenna. The inductance of the helix acts like the loading coil for electrically shortened dipole antenna. Normal mode helical antennas have maximum radiation at right angles to the axis of the helix and they are omnidirectional. Rubber ducky is the typical example of a normal mode or broadside helical antenna. Being electrically shortened antennas, gain and range of communication of rubber ducky is less than that of a full-sized antenna, as every ham radio operator is fully aware. Monofilar helical antennas have linearly polarized radiation pattern parallel to the axis of the helix. Bifilar or quadrifilar helical antennas can have broadside circularly polarized radiation pattern. Diameter and pitch of the helix are comparable to the wavelength in axial mode or end-fire helical antennas. These are directional antennas radiating off the ends of the helix along the long axis of the antenna. Radiation pattern is circularly polarized, and end-fire helical antennas are used for satellite communication as the antenna illustrated here. As you can see, there is a ground plane reflector at the base of the antenna. Today we will discuss about the importance of ionosphere in radio communication. Ionosphere is a layer of the atmosphere which gets ionized mostly during daytime due to the effect of sun rays, and it is situated high above the atmosphere, almost in the thermosphere. It may extend into the exosphere above and mesosphere below. When radio waves reaching the ionosphere has a critical frequency above which it will just radiate out into the space. That is why VHF and UHF radiate straight to the space. But HF, below that critical frequency, will be reflected back to the earth and to the ground, which will skip around the earth and produce long distance communication. These are the layers of the atmosphere. The lowermost is the troposphere. That's the place where we are all walking about, lowermost layer of the atmosphere. Then comes the stratosphere. Beyond the stratosphere, you have the mesosphere. Still beyond is the thermosphere. And outermost layer is the exosphere. As you go up from the Earth, due to the reduced effect of gravity, the atmosphere becomes thinner. So the number of air molecules will be least in the exosphere and maximum in the troposphere. Usually, temperature also goes down as you go higher up. Our region of interest for radio communication is the thermosphere because the ionosphere is mostly located in the thermosphere. But ionosphere is not a static situation. When sun comes up, more of solar ionization occurs in the thermosphere or that region of the atmosphere. So that ionosphere can extend sometimes out into the exosphere and down into the mesosphere. It may range from 60 to 300 kilometers from the surface of the Earth. So it is not a static condition. At daytime, there is more ionization. At night time, ionization is less. Similarly, when the solar activity is more, with more of sunspot activity, ionization increases. Currently, we are in solar cycle 25 and we are reaching the maximum in another 1 or 2 years. When the maximum is there, ionospheric condition will be better for long distance propagation and you will have more of ions in the ionosphere due to solar sunspot activity. These are the layers within the atmosphere by daytime and nighttime. Lowermost is the D layer. D layer is the one which absorbs medium waves, so that medium waves will not get reflected by the ionosphere and depends only on local propagation, that is ground wave propagation. But at night what happens is that the D layer disappears due to decreased ionization. Then medium waves can penetrate up to the E layer and get reflected like this. Suppose this is a transmitter here, it can go up and then get reflected. That is why you would have noticed that medium wave stations at a longer distance can be heard at night with better clarity. And E layer is the one which reflects the short waves usually, because short waves will not be absorbed by the D layer and they will be reflected by the E layer. Still higher frequencies in the short waves will go beyond the E layer and get reflected from the F1 or F2 layer. The difference between F1 and F2 is that when there is higher ionization during daytime, F layer splits into two, F1 and F2. At night, when the ionization decreases, these two layers fuse together and there is only one F layer at night and there is only one E layer. There is no D layer at night, E and F only at night, while at day they have several layers. One is D, which absorbs medium waves, E, which reflects short waves of the lower range, F1 and F2, which reflects short wave of higher frequency. When the frequency goes beyond that range, that is beyond say 30 megahertz, usually it may not get reflected by any of these layers and it will go straight into space. That is why for VHF and UHF and higher ranges of frequency, you do not have this skywave propagation from the transmitter into the sky back to the earth. That is skywave propagation, which I will show in another diagram. These are the sky waves which we are talking of. This is the representation of the ionosphere and this is the transmission. When there is a transmission, the ground waves cover only a small region. This is more commonly seen for ground wave, is more commonly seen for medium wave transmission. And for short waves, when it is going at a critical angle, it will get reflected off the ionosphere and come back to the earth at a distance. This distance is known as skip distance. And the distance between the end of the ground wave propagation, that is here, and the place where the nearest skip of the skywave occurs is known as skip zone. The skip zone, importance of skip zone is that if you have a radio here, nothing will be heard in this region. This is more when the frequency increases. For example, for a 7 megahertz wave, maybe it will come down here. And for a 14 megahertz, it will have a higher hop. That's why you would have noticed that you will hear long distance stations better on 14 megahertz and short distance stations better on 7 megahertz. In amateur radio, 7 megahertz is most popular for short distance communications, while 14 megahertz and higher bands are popular for long distance communications. That is because of this skip zone and skip distance. The skip zone and skip distance are not static. It will change according to the ionospheric ionization conditions. It will be different at daytime and nighttime, as well as between morning and noon. There will be difference because ionospheric ionization conditions changes. Half-wave dipole antenna fed at the center is the commonest type of dipole antenna, and its length is almost half of the wavelength of the frequency for which it is meant. So the total length of a half-wave dipole antenna for the 40-meter amateur radio band will be almost 20 meter. The space needed for the antenna increases as you go down along the amateur radio bands. I had the opportunity to use both 40-meter and 80-meter half-wave dipole antenna earlier, but I'll have to struggle to get even a 20-meter half-wave dipole antenna up at my current location. Maximum radiation from the half-wave dipole is perpendicular to the conductor with almost zero radiation along the axis of the conductor. This would also mean that it would act as an omnidirectional antenna if installed in a vertical position. But installing half-wave dipole in a vertical position would not be easy for a lower amateur band. In my earlier days of ham radio, I used to simply tie the half-wave dipole across two tall coconut trees using plastic twisted flex threads. Threads would be tied to stones and flung up on top of palm leaves and pulled up in a pulley-like fashion. Of course, those half-wave dipoles used to sag in the center due to the weight of the connecting coaxial cable, and it would be almost a V antenna. A half-wave dipole antenna can also be used at odd multiples of its fundamental resonant frequency. Thus, a 40-meter or 7 MHz half-wave dipole can be used for 21 MHz but not for 14 MHz. It will act as a 3x2 wave dipole antenna at 21 MHz. The directional gain of a half-wave dipole antenna at the resonant frequency is about 2 dB. Most of the antennas which radio amateurs use on HF, VHF, UHF bands have linear polarization, either vertical or horizontal, and are not ideal for satellite communications. Polarization of an antenna is the direction of electric field produced by the antenna and determines the direction of transmission and reception. In circular polarization,